Okay, hello students, Chemistry 311. So we're going to discuss in this video quantum mechanic topics. We will start with looking at electrons moving. So when an electron moves, right, it will behave like a wave. So electron is a particle, very light particle, has a mass of 10⁻31 kilogram, and when it moves, it will move like a wave. Okay, so if it's a wave, then the principle of wave mechanics applies to that motion. So if it's a wave, then it will have a wave function description, okay, and it will have a wave vector. Okay, so a wave vector is a value that describes the direction of propagation of the wave. Okay, and the wave vector has a formula of 2 pi over lambda, right? So because we will deal with movement of electrons in our examples, so we will use the mass of electron to describe it. So when if electron moves at certain speed, it will have a momentum p, and which this p, according to de Broglie, is Planck constant over the wavelength, right? Okay. Right. So then I can describe lambda as p h Planck constant over p. Okay. Now if I take this definition together and I substitute lambda here, so I will get that the wave vector will equal 2 pi over h over p, and then this will become 2 pi over h times p. Okay, so 2 pi over h is is 1 over h bar. So this can be simplified to p over h bar. Okay, this is the wave vector of a moving electron. Okay, so we also know that momentum is mass times speed or velocity, right? So the kinetic energy of a moving electron can be described as half mv squared. V is the velocity, m is the mass of the electron, right? So considering that we know momentum is equal to m times v, so I can substitute this with momentum, which becomes squared. Okay, this is because v will be equal p over m. Okay, substituting v as velocity here, and this will become p squared over 2m. Okay, the kinetic energy of a moving electron. Okay, now we know from here, from this relation, that momentum is h bar times k. Okay, so we can substitute the description of kinetic energy into h bar squared k squared over 2m, right? So this is the description of kinetic energy of a moving electron. So it has this is a constant, it has a electron has a mass, it's also a constant, so now this depends on the wave vector. The wave vector is a function of a wavelength, right? So the higher the wave vector value, then the higher the kinetic energy, right? So if I wanted to describe the wave vector, this will be square root of 2me over h bar, right? Okay. So we have a description, a correlation between a wave vector and energy, kinetic energy, right? Right, so now let's look at the example. Okay, let me see if it's open. Let's look at the example of a free electron. Okay, a case of free electron, right? This is a case where an electron is moving in one dimension. We will just limit this discussion to one-dimensional. So electron moving in one dimension. So we know that electrons are like all objects, according to the de Broglie principle, that it will move in a wave-like manner. All right, and I will just give you straight to the solution that the wave function of a free electron is a constant times exponents of power of I, k, and x. Okay, x is the distance at which it's traveled, it's one-dimensional, and k is a wave vector, and I is an imaginary number. Okay, right. So if we wanted to describe the total energy of a free electrons, right, if we use a wave function, we have to use total energy operator, right, which is the Schrödinger equation. Total energy operator. So this is minus h bar square over 2m times the second derivation of the wave function plus function of the potential energy equals to E, a constant or a product of the operation from the operator times the wave function again. Right, so let's just limit the condition that throughout the distance of x, okay, where the electron is freely moving, the free electron is freely moving, the potential energy is 0 all around this x direction. Okay, so this will cancel out. So then we will have only kinetic energy. Okay, so we have to do the second derivation of a free electrons. That will give you the product of a second derivation of this would be A times I k square and E I k x. Okay, and you have this constant comes here. Okay, so second derivation of the wave function is this, and this will be equal to E. Alright, so I k square will give you minus k square and kx. So I will just isolate this, and here you get positive minus and minus k square h bar square over 2m a I k x. Alright, equal to E psi x. Okay, now if you look at this form, this is exactly the same as this one, which is the wave function, the original wave function. And here, this value then should correspond to the total energy of the system, of the free electron system. So in this case, because we assume, or we set the condition that the potential energy in the x direction of the electrons traveling is 0, so this is purely only kinetic energy. So the E is equal to k squared h bar squared and 2m, right, which is similar to what we have derived for the general properties of a moving electron, right? sorry, this one, kinetic energy h squared h k squared over 2m. Okay, so which means that the energy of the free electrons can be of any value. There is no limitations, right? Any wavelength, because k here, keep in mind that k is 2 pi over lambda. So the free electron can have any wavelength. In that case, it can have any energy, any kinetic energy. Okay, so as we're discussing on free electrons, with this wave function, we describe that the energy of a moving free electrons has this value, with k is equal to square root 2 me over h bar, and k is a wave vector, which is equal to 2 pi over lambda. Now, according to this formula, k can have any values. Thus, the energy of a moving electron can have also any values, right? So if we try to sketch it, electrons moving from free electrons moving from 0 to L, it can have this wavelength, or it can have faster wavelength. Okay, my drawing is terrible, but you get the point, right? So also keep in if you pay attention, aside from the fact that the frequency of the wavelength can be of any value, this is high frequency, this is lower frequency. For example, at this point, the value of the wave function can be of any value. It can be here, you can start here, 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 doesn't matter, right? You can have any wave function, any position at 0. Now, this translates that the energy, because the wavelength can be of any value, the energy can be of any value. So if we were to plot the energy profile of the free electrons, it can have this value, that value, this value, that value, this value, this value. Just going to draw continuous line here, right? Because you can have any lambda value, right? So it will be a continuous energy profile is continuous for free particle. Great. Now,